So, what if an AI could see our world, not as one big, chaotic mess, but as a series of distinct, understandable layers? Well, today, we're going to dive into that incredible idea and see how it is literally changing everything.
I know, right? It sounds almost impossible. How could one single concept connect all of those things? The answer, it turns out, is in a really elegant idea: being able to see any complex system in layers. It's a perspective that unlocks secrets that were hiding in plain sight the whole time. Okay, let's break this down because the core idea is actually super intuitive. Think about looking at a picture of a city. The low-frequency layer, that's the big picture, the overall structure, the general layout of the streets and skyline. The mid-frequency layer, well, that's where you find the main objects, the individual buildings, the cars, the parks. And then you have the high-frequency layer. That's all about the teeny tiny details, the texture of the bricks on a building, the leaves on a single tree. This AI learns to see everything in the world this way. So, how do you actually get a machine to see the world like this? I mean, it's not like you can just ask it nicely. No, you have to build an architecture that basically forces it to organize information this way, right from the get-go. The secret sauce here is a technique called, and it's a mouthful, differentiated regularization. But don't let the name scare you. Just think of it like this. You're telling an artist to be incredibly precise with the overall composition of a painting. Get the big shapes right. But then you let them get a little more loose, a little more free with the fine textural brushstrokes. You're basically setting different levels of strictness for each layer the AI is learning. And here's exactly how that plays out. As you can see, the AI has to follow very strict rules for that low-frequency big-picture layer. The global structure just has to make sense. But as you move down to the high-frequency details, the rules get way more flexible. This gives the AI the freedom it needs to capture all the noisy, complex textures of the real world. It's this gradient of rules that perfectly teaches it how to separate the fundamental structure from all that fine-grained detail. And this is the moment where a clever trick for images becomes a revolutionary tool for all of science. Researchers suddenly had this aha moment. They realized this method of seeing in layers wasn't just for pictures. Nope. It could be applied to pretty much any signal, any kind of data, anywhere. It turned a neat idea into a universal scientific instrument. So they gave it an official name, the Universal Signal Decomposition Framework, or USDF for short. The best way to think about it is like a universal lens, a consistent, principled way to analyze the multi-layered structure of reality itself, from the biggest, slowest-moving trends all the way down to the tiniest, fastest little fluctuations. Okay, so what can you do with a tool like this? Well, for starters, you can decode brainwaves. The USDF can automatically pull apart the slow, low-frequency signals of our overall cognitive state, like whether they're focused or daydreaming, from the fast, high-frequency signals of raw perception. It's like separating what you're thinking about from how you're thinking. Or how about this? It gives robots a kind of hierarchical common sense. The low-frequency band handles the big, high-level goal, like go to the kitchen. Meanwhile, the mid- and high-frequency bands are busy managing all the little details, the fine motor commands needed to step over an obstacle or adjust its grip on a glass. In medicine, this could completely change how we read an ECG. The low band can spot long-term heart rate trends over hours. The mid-band can identify the rhythm from beat to beat. And the high band? It can detect tiny, subtle changes in the shape of a single heartbeat that might signal a problem. That's a level of detail that was just lost in the noise before. And when you zoom out to a planetary scale, its power becomes crystal clear. The USDF can take decades of climate data and just cleanly separate the long-term, low-frequency signal of climate change from the mid-frequency noise of seasonal cycles and the high-frequency spikes of individual storms. It gives us an unbelievably clear view of our changing planet. But of all its possible applications, there is one with a really profound, immediate moral weight: using this new way of seeing to uncover hidden corruption in our public financial systems. So that's the big question, isn't it? How on earth does separating data into different frequency bands actually help you find evidence of something like financial crime? It's because different types of corruption operate on completely different timescales, as you can see right here. The low-frequency band, that reveals the slow, systemic rot,
like an entire institution being captured, something that plays out over decades. The mid-frequency band catches procedural stuff, like bid rigging schemes that might cycle every few months. And that high-frequency band, it flags the fast, transactional fraud, like a single fake invoice. Before, all of these signals were just hopelessly tangled together. But now you can see each one clearly, in its own separate layer. This creates an incredibly powerful new process for investigators. First, the system just breaks down years of financial data. Then, it scans each layer for anything that looks weird, patterns that just don't fit. And finally, an investigator can immediately pinpoint the type of potential corruption just based on which layer that red flag popped up in. I mean, this is a total paradigm shift. It turns the search for a needle in a haystack into a targeted, evidence-based investigation. So when it's all said and done, this is so much more than just a clever algorithm. It's a fundamentally new lens for looking at any complex system out there, and it's forcing us to totally rethink how we analyze the world around us. This quote from the original research really just nails it. The universe operates at many scales. Our analytical methods should too. From our own brains to our planet's climate, reality is multi-layered. And this framework gives us, really for the first time, an analytical tool that actually matches that layered reality. It allows our methods to finally catch up with the very world they're trying to describe.
And that leaves us with a pretty fascinating final thought. We now have a way to teach a machine to see the hidden structure in almost any system you can imagine. The only real question left is, where should we point this powerful new lens next? And what hidden truths are just waiting there to be revealed?